Hey guys, I'm Lou, and today I'm going to be discussing a research paper about voice augmented manipulation, or VAM for short. This paper was from the Mobile HCI conference in Munich, Germany from 2013. So it's a fairly new research paper, and I think what they were discussing is very relevant today. Also have a link to the paper here if anyone is interested in reading it, but I originally found it on the ACM Digital Library. So what exactly is VAM and why is it important? Well, it gives you audio control over a particular function on a mobile device. So for example, you'll see in the next slide, there's certain actions that we can do once we initiate them with VAM. Of course, it is supplementary, so it doesn't replace, all your touch input on your phone. There's certain things that you still need to do first. And some of these functions can be things like zooming in or out. And this essentially alleviates repetitive gestures that often come with touching the screen only. And ideally, I think that this can open the door for new modes of interaction with our mobile devices, which is a very interesting concept in and of itself. So, the general idea of VAM is that it uses these paralinguistic sounds, which could be tones, volume, intensity, or pitches, in order to control the functions on a phone. So, this is done first by either initiating the action through a gesture or holding down a button. So look here, we have first the button hold. So the first thing you would do is you would hold down, for example. Now as you're holding down, this is telling the pre-programmed VAM action that you're now in the down function. And once down is being held, you can just go ah, and your phone would scroll down, the screen. So if you're on a website, for example, that site would scroll down. Now as soon as you release the button, it's no longer going to give you that control. Or you could say stop. Now, if you want to initiate a new function, you might hold down up, and assuming that it's been programmed into the phone, holding down up will take you back up. Now, if you have gestures programmed, this is a little different. Instead of holding down the button, you would first initiate the VAM function by simply swiping down. Once you swipe down, the phone knows that you're now using that function. So anytime you say ah again, it will scroll down. Likewise, if up has been programmed, then you swipe up, saying ah will move you up, or again you can say stop. So these researchers tested this with two different types of interaction scenarios, and they used a 4-inch phone with a 480 wide by 800 long screen. So for the first test, they wanted to ask 20 college students to follow a sort of map path, which would simulate, using a real map like Google Maps to navigate somewhere. And they decided to test this by testing, VAM with the button hold, VAM with the gesture, and then just simply sliding around without any VAM control at all. So, in order to, make this an experiment and have measurable variables, they decided to make that the total path that the students would travel would equal 8,000 pixels. So if you started here, and your whole total path was here to here to here, and say all the way around here, by the time you got here, that had to be 8,000 pixels total. And the maximum distance between each point could only be either 200 or 800 pixels. So there was a bunch of random maps, and they did this for 3 sets of maps, 3 times each, using all these different approaches. So once the college students completed their tests, they averaged up all their times going through each set of 3 different maps to navigate. And I think the takeaway here is to realize that VAM plus touch, or the gesture, is perhaps equally or more effective than just sliding one's finger. And we can see that the times between the two are back and forth. It looks like holding down a button and then going to VAM is not effective. It's almost, in a lot of cases, double the amount of time to complete the task. So I think that this gives us a good base point that there's something worth, pursuing here with VAM. Now, the second test was a little different. They asked the students to perform the zoom function on the device. And in order to test this, they decided that they would create a target that was 40 pixels in diameter, but the only way it counted as a successful zoom in is if they zoomed in far enough that 30 pixels of it filled the screen. And they had 4 different targets, but the only time you could see the next target was when you zoomed back out, because each target that was generated was always 2400 pixels away from the previous. So you zoom in, you zoom back out, and then the new one you see over here. You zoom in, you zoom back out, and the new one's down here, and you keep doing this. And they also decided to test this with four methods this time. They did the pinching, which we're all familiar with. We use that in Google Maps, iMaps. They did the sliding bar, something more we see on PCs. You just sort of slide it in and out. Usually, I think Google Earth has it actually too, where in the software you can kind of just slide the wheel in and it'll zoom you in, and vice versa for zooming out. They also did VAM for touch, so you do the zoom in function, and then you can say and it'll zoom you in. And they did the VAM with buttons, so if you want to zoom in, you would hit the zoom in, and then you would say and it would zoom you in. So these four different tests were conducted, and then let's take a look at the results and see how they fared when they were averaged up with the 20 users. I have to say here that the results were counterintuitive of what I expected. I was really surprised because according to their results, the pinching actually took the longest to complete. So navigating to these four targets and pinching in and out, now that didn't seem right. And according to them, the sliding bar was the quickest. The logic that I was kind of gathering through their paper, and I guess they were trying to make this claim at one point, was that using one hand versus two hands may be the case. So if you have that hand free, you're just sliding in and out constantly with your thumb. That could be the quickest way. But it's also worth noting as well that VAM and the button, so you tap the zoom in, you can just say to zoom in. That was still very fast, and that was almost as fast as the sliding bar in all the cases. And then VAM and just the touch gesture by itself was moderately fast. It was kind of averaged out both the longest and the shortest times. So a very interesting results here. These tests and this research is all really interesting, but what else can we do with this? What is actually the point of this? Because in the paper they're really focusing on using it, what I think is for maps, and maps are great. We've basically replaced our GPSs with our smartphones to navigate and get around. So there's plenty of reason to study this, but you can also use this for other things. So I was thinking, create sort of like a mount for your phone. So if you're kind of like lying down and you don't want to constantly be touching your phone, you can just have this sort of extension that, sounds silly, but maybe comes out of the wall and anchors your phone to it, and then you tap it, and then you do your gesture, and then you tap it again, and you're not constantly holding the phone, so you can relax more. And this would work great with tablets too, because tablets are quite heavy, or maybe a pound or two, and that would get tiring to hold up. But if you're watching a movie on your tablet, you can easily control it, or if you're on YouTube and you just want to navigate through certain things. And you can also, of course, use it to just navigate the main menu, your dock, and just open and close apps once you have a certain a gesture set up for it. So there's a lot of ideas that I think that can be further developed off VAM, but this is a good starting point, absolutely. It's also important to ask some new questions, because in this paper, there's things I think that they open the door to, but they definitely don't close, or they don't have a chance to close, and it's hard to close them just in a discussion. But let's just hit on the fact that they mentioned this, and I think it's worth mentioning even more, that the social acceptance of this. So if you're in a public place and you're using your phone, are you going to be willing to make these and varying sounds in order to control it? You're probably more than likely going to shy away from doing so, unless, and this is what I think is important to clarify and answer, acceptance. So if more people are doing it in the first place, meaning they can introduce it quicker and prove its value more quickly, then it will become more acceptable. And the key to doing that is to implement it. Get it as fully functioning as possible on the back end, so it's completely ready for adoption, and then people will pick it up and use it, just how they pick up and use things like Siri now. People aren't embarrassed to talk to Siri in public, but this needs to sort of become an extension of that, or Google Now, or Microsoft's Cortana, whatever the current voice control is. This is not directly using words, but using sounds, and if people can accept that, then I think it'll be quick to adapt. I was also thinking, how would I run this if I had the same resources? What would I do differently, or what else would I try? And I was thinking, well, as I was saying before, let's try a different program entirely. So let's try testing to control your music, your MP3 player. Have it such that when you tap, when you open the library up, you can see all your songs, and once you launch the down gesture, you can navigate through your songs without having to keep stopping. So if you have, 1,000 songs and you have, only 20 songs on the screen at once, will take you down another 20. And it sounds silly, but that's the idea behind this. So this is another way we can implement it. And also, I think, as I was saying before, try the social acceptance test. If you're going to put all this effort into a new idea, you might as well try getting it going in the terms of acceptability, because I think it's worth it. It's a very interesting concept. VAM is also important because it relates to other research. It marries, computer programming on the mobile end with human-computer action in general, which is awesome. And it also studies things in terms of how to program for proper loudness, softness, the timbre, the pitch, and then hardware variables, software variables, environmental influences. All these things have to be accounted for and researched so that when you implement this system, essentially and hopefully, in a commercial environment, all these things will be properly studied and properly integrated, so the system works as it should. I also think it's worth discussing, at least in brief, what was positive and what was negative about this paper and the research. On the positive end, it was definitely concise and it was well articulated. It showed everything it needed to show. It got through a lot of interesting ideas, and it certainly backed up its ideas with evidence. It had lots of nice graphs. It visualized everything for you, and I tried to show you guys as much of that above with the earlier slides, but it wasn't perfect. And I think the problem with it was it wasn't critical enough of itself. As great as these ideas are and as fascinating as they are, I don't think it challenged itself enough. It didn't question the motives behind what it was doing. And I also think might be a silly point, but I think the screen that they were testing on should have been bigger. Most phones today that people are using have at least a 1280 by 720 screen, if not 1920 by 1080. Even some of the newer ones are higher than that. So the resolution, I think, should have been tested on something that's more applicable to most smartphone users' screens. So let's sum this up. And why did I pick this paper? Let's talk about that briefly. I think mobile devices are becoming essentially people's main computers, or an extension of that at least. So there's so many ways to interact with them. Thinking about them, just in one light, it's just a touch device, kind of limits our understanding of what they can be and what they can do for us. So I think this was a great paper that really showed the voice manipulation beyond just things like using words, but using our own, our human sounds, because we make more than just words. We can, speech is built off sounds first, not words. So if we can get that, primitive ability implemented in our touch devices, then I think it really just adds a whole other layer of interaction with them. And I think this is a great step towards what else can we do with these devices as time goes on. So with that said, I want to thank you guys for taking the time today to listen. Please post any questions, comments, concerns you have in our discussion forum. And I look forward to hearing everyone else's presentations. Thanks.